of functions when we're talking symmetry. Okay, one is called an odd function and one is called an even function. All right. The definition of an odd function is a function that has rotational symmetry about the origin. Algebraically, all odds have the property f at negative x is equal to negative f at x. What this means is, if you think of the positive values of x, if I change these values from positive to negative, my y value is going to be negative. All right, so what was once negative, say negative a half here for y, so say this is negative, this is 1, negative a half. So what I'm saying here, if I change that x to negative 1, so I go this direction, my y value is going to flip. Okay? So you get this symmetry about the origin. Okay? What was once very high positive y value gets switched to a very low y value at the same value of x. Okay? That's just become negative. All right? That's called an odd function. You gotta kind of look at it a while to really understand it, but it's kind of like diagonally symmetrical. You want to think about it like that. Okay? An even function is a lot easier to recognize. Okay? Whatever the value is on the positive value of x, that negative value of x has the same value of y. So, for positive x equals, let's say 10 over here, I have a really high value of y, say 25 or whatever it is. I go to negative 10, my y value is going to be the same value. Okay? Or another way of looking at it is just reflected in the y-axis. Okay? The y values stay positive, and if they're negative, they stay negative. Okay? And the way that's written in set notation is if my function of negative x, so my negative x values are the same as my y values, my positive y values. Any questions there on odd or even functions? Finally, a continuous function we know it has no holes or breaks. So it's a straight line, there's no discontinuities, and we spoke about that. Discontinuity is a break in a graph, and it's called a point of discontinuity. So it can be either an asymptote like this, a vertical asymptote, a horizontal asymptote, or it can simply even be just an open circle, okay? That could mark a discontinuity, okay?
Yeah, we cancel the triangles.
Okay, so this could be a graph of y equals x, where x, or where y cannot equal, say, 1. So you have a hole at y equals 1. Okay, so this would be also a discontinuity. All right, so now if we go back to our parent functions, so we can say the symmetry, whether it's odd or even.
Excuse me, Mr. Mills?
Hi.
Sorry about it. Is Christian there?
Yes.
I can see him in student service. Just for a moment, please.
Sure.
Thank you.
So if we look at symmetry now, we can see that this is kind of reflected diagonally, or the y values that were positive are now negative for the same value of x. Okay, or the negative value of the positive value of x. They're now negative. So this is an odd. That's an odd function. This is an even function. It's reflected upon the y-axis, so the y values are the same for the positive and negative x values. That's even. This is odd. Again, it looks like it's reflected diagonally, but another way to think of it is the positive y values for the same value of x are now negative. Even function. Let's just do these last ones here. Odd or even function here, Nicholas. Yeah, it's neither. It's not reflected in any axis. It's not symmetrical either way. Okay, this one. This one? Who said even? Neither. Okay, yes, neither. Yeah, good. There's no symmetry about it, right? There's nothing that's common. And this one, there's definitely is a symmetry about it. The positive values of y are now those same values but negative. So it doesn't look as clear, but it is kind of a diagonal reflection of each other. Okay, these were negative, they become positive, positive or negative. All right, so that's an odd function. And finally, the last thing we need to worry about is the end behaviors. What happens at the ends of the graph? So what happens here? What happens here? Okay? So this is pretty self-explanatory. As x approaches positive infinity, y is going to approach positive infinity. As x approaches negative infinity this way, y is going to approach negative infinity down this way. Who wants to do this one? The end behavior. Okay, Lyndon?
As y approaches...
No, it's always x first.
As x approaches negative infinity, so does the y approach negative infinity?
No. Y to approach negative infinity would be down here.
So I mean positive infinity.
Right, so as x goes negative infinity, y goes positive infinity. Yeah, this one?
As x approaches positive infinity, so does y approach positive infinity.
Good. Okay, next one. Ramon? What's happening at the end here?
It's decreasing.
You're right, it's decreasing. So as x approaches positive infinity, what is y approaching?
I don't know.
So as x goes this way forever, it's getting closer and closer and closer to what value of y?
Oh, 0?
Good, 0. So as x goes to infinity, y goes to 0. Okay, so see that, the first difference. Can do the other side, Ramon? As x goes to negative infinity, y goes to?
0.
Good. Okay. Next one, Alan. As x goes to infinity,
Y goes to infinity.
as x goes to negative infinity,
Y goes to infinity.
good. Next one, Jesse.
As x goes to infinity, Y goes to infinity.
Yes, good. And as x goes to negative infinity,
It doesn't continue.
right, or y, if it goes there, it's ending at 0. So you could have put just even none there. There's no kind of end behavior happening there. Daniel.
As x goes to positive infinity, y also goes to positive infinity.
Good,
And while x goes to negative infinity, y goes to 0.
good. And this one, last one, always the trickiest. It's oscillating between 1 and negative 1. So there's no kind of determined infinity behavior because we're just going up and down forever. Okay, any questions? All right, so that's a big handout. That'll be the majority of what's happening on your quiz. Your quiz, by the way, is from 1.1 to 1.3. It's in your daily plan. So this is the last lesson that will be on the quiz. Okay? And the quiz is going to be on Wednesday. Okay, so not tomorrow, but the next day. Tomorrow we're doing 1.4. The quiz is on Wednesday. It's only going to cover 1.1 to 1.3. All right, so we're going to go through the examples here quickly. Now, we should know everything about these parent functions. All right, so we're trying to match the parent with the characteristics of its graph. Who's talking over there? Is that Joseph? Okay, help us with the first one, Joseph. What's the characteristic of this graph? Only one card per card. So you're matching the graph to one of its characteristics.
The domain of x is somewhere around.
Yes, good. So this one goes with this one, you're saying? Okay. And that's true, but that's also true for some of the other graphs as well. Okay, so it's also true for this graph. It's also true for this graph. And it's also true for this graph. Okay, so we just got to be aware of that. Okay, so we got to be aware that we can get rid of these other three with the three other characteristics. Jason, this graph, what's a characteristic for it? Of the three remaining, let's say.
The range is an element of all real numbers, and it must be greater than 0.
Good. So this graph goes with this graph. Could also go with this graph. Right? Oh, sorry. Yes, you're right. My bad. Sorry, Jason, yeah, this is incorrect because of that equal sign. So because this is an asymptote, even though it looks like it touches 0, it actually doesn't. Okay? So this graph here would actually go with this one. Does it make sense?
So that's it says equal to 0. That's the last one.
Oh, yeah.
Yeah, this one equals 0, this one equals 0. Yeah. No, this one goes with this one. Alright, second one goes with the last one somebody said. As x goes to negative infinity, y goes to 0. That's right, yeah. That goes with that one. And then we're just left with this one, infinite number of zeros. And we know that's the case. Why? Because we have a 0 there, a 0 there, a 0 there. And we know it keeps crossing 0. Okay? So this one goes with this one. Any questions? That's pretty easy. Alright. See example 2. State which of the parent functions in this lesson have the following characteristics. So I'm going to bring them up here again. The parent functions. So which parent functions have domain XER? So we have domain XER, domain XER, domain XER, domain XER, domain XER. So there's 1, 2, 3, 4, 5 of them. So they list them here. 1, 2, 3, 4. Okay, they list them. They only cross out these two because they have domains that have restrictions. All right? So these are the 5 that we have, and then it asks us for the range between -1 and 1. Which parent function has that range? It's pretty easy, right? We don't know this. Yeah, Mark?
Sin x.
Yeah, we know that sin x is the only one that oscillates between 1 and -1. So only the sine function has the range between 1 and -1. So I'm curious why they crossed out the sin x here. This is clearly a mistake here. Okay? It should be this one. For some reason they left f at x equals x. This is the one we wanted. They gave the right reason, but they crossed out the wrong one. Okay? Any questions there? Alright. Example 3. Which of the following characteristics of the parent function? Remember, this graph looks like this. That's our graph. So which are the characteristics of this graph? The graph is decreasing for all values in the domain of p at x. So is this graph decreasing at all, ever? No, so not this. The graph is continuous for all values in the domain. Is it continuous for all values in the domain? Yeah, so it's this. The function is an even function. Is it even or odd? No, there's nothing symmetrical about it, so it's not that. And the function has no zeros. Is this true? Yes, because it never crosses y equals 0. Done. If I'm totally off on the screen, let me know. I don't know if I was on there. Last one, determine a possible transform parent function that has the following characteristics and sketch the graph. So domain equals XER, so there was 5 of them to choose from. So that one doesn't really help us too much. Okay, it could be all of these. The next one says, the range is greater than and equal to -2. So I'm going to look at the range, and I'm going to see a parent function that has a very similar characteristic to that. So I see this one, greater than and equal to 0, greater than and equal to 0, and greater than and equal to 0. So it tells me that if I have a vertical translation of 2 units down, all 3 of these could satisfy what I'm trying to get to. Agreed? So there's still 3 possible. They all have, actually, sorry, not this one because it doesn't have XER. So there's 2. It's between this one and this one. Okay? Increasing on the interval -infinity to 0. Yep, this one works. And increasing from 0 to infinity. This one works. This one also works. Okay? They have the exact same characteristics, these 2 graphs. So I would say that both of these could be a possible graph, parent function for this. Okay? And that's what they conclude here. Here are the two graphs at the bottom. Okay? So all they did was take that graph, the parent function, and translate it 2 units down, and they satisfied this. Okay? Everything else was satisfied from the parent function. Okay? So we translated parent function y equals absolute value of x and y equals x squared 2 units down. Okay? Any questions there? All right. So finally, in summary, functions can be categorized based on their graphical characteristics: domain and range, x-intercepts and y-intercepts, continuity and discontinuity, intervals of increase and decrease, symmetry, and end behavior. I hope all of these terms now make sense to you. Any questions about what any of them mean? Okay, finally, need to know, given a set of graphical characteristics, the type of function has these characteristics can be determined by eliminating those that do not have these characteristics. That's pretty self-explanatory. Some characteristics are more helpful than others when determining the type of function. What's the least helpful characteristic of a function? What do you guys think? If I gave you a characteristic for, out of all these are the characteristics, what's the least helpful to isolate one parent function? Yeah.
Maybe the range.
The range, yeah, I would probably say the domain more so than the range, but you're close. The reason why I say the domain is because so many of them share the same domain. Okay? I've told my students before, if they're on a test and they're clueless about the domain, put XER, because a lot of times it's XER. Okay? It's better than nothing. You know? 5 out of the 7 parent functions is XER. Okay? All right, that's the end.